finally, you get embedding with time signal. You mean x1 and x2 and x3, and now you're ready to pass it to the encoder. So the first part is just positional encoding. And T1, so these positional encoding, so T1, T2, T3, so you add x1 with T1, you add x2 with T2, you add x3 with T3, and they follow a specific pattern that model learns. So which helps it determine the position of each word, or the distance between words in the sequence. For example, your T1 could be 0011, your T2 could be 0.84, 1.54 and 1, and T3 could be 0.1, 2, 4, 2, and 1. So each row contains 512 values with a value between -1 and 1. And if you look at the code, the function, the Python function that you have written is the name of that is get timing signal 1D. First, your TensorFlow, you concat sine and cosine, and then your signal, you do a padding. TensorFlow, you use padding, and then you reshape it. You reshape your final variable to one length, because this is the input of this function, length, and then channels. So these two are the inputs of this function. And what is doing is just calculating these numbers. Sign of position, like 0, 1, 2. For example, 0 is the first word of the sentence, 1 is the second, and so on. So position divided by 10,000, as is written in the article, attention is all you need, to the 2i over d, but you can choose your favorite one. For example, when I say French mathematician, French is p equal to 0 is position, first position, and then p equal to 1, the next position, and so on. And also, you do it for 2i plus 1 for cosine. So p divided by the same thing. And remember, I is a list with length d. And so, it's very simple. But I didn't talk about decoder side. Let's talk about decoder side. The output of encoder is transformed into a set of attention vectors, K and V. So decoder uses these vectors to focus in appropriate places in the input sequence. So you pass the keys of the encoder and the values of the encoder to the decoder section. So the decoder part, so because it's a stack, so just put another decoder, lots of decoders, and finally you pass it to a linear plus softmax. And what you receive is the German translation. So it becomes Ich bin Farshad. For example, you give English, I am Farshad, and then it does the opposite thing. It translates to German. So this encoder-decoder attention is like multi-headed self-attention, except it creates its queries matrix from the layer below it and takes the keys and values matrix from the output of the encoder stack. So the final linear in softmax layer is what I want to talk. So the linear layer projects the vector produced by the stack of the decoder into a much larger vector. Call it a logits vector. For example, you have a decoder stack output. You give it to a linear. So it depends on the size of your vocabulary. For example, let's say we have 10,000 words, English words. So this is, they call it logits. And then, if you pass logit to softmax, you get probabilities because it's between 0 and 1. And those probabilities add up to 1. And so you have log probabilities, and you have vocabulary size, as I said, is just 10,000. And this is what you do in the decoder side. And training is very easy. In the training, we are training it on a labeled training dataset so we can compare its output with the actual correct output. So I explained transformer model, but there are many articles in order to handle the problems of transformers. For example, when I look at this transformer model, I realize that when the sentence becomes very big, it cannot handle those things, just like LSTM or any other sequencing model, because the system needs to be scalable. So the model needs to be scalable, so transformer has some problems. And some people they wrote an article called Sparse Transformer. We have graph attention, but there are lots of different graph transformers, and each of them, they mean different thing. Some of them is just related to the idea of graph sage, something like that. So each person has a different meaning when they combine graph with the idea of transformer. And for example, I'm working on a model of transformer that can handle long-range dependencies. Because if you have a very, 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 very long sentence, how do you deal with all of these dependencies? So you need some kind of sparsity. Also, you need to handle that in a different, non-traditional way. So you can have your own variants of this transformer approach. And also in computer vision, now that's it is, they use convolutional neural networks a lot, and because it's a local, it captures local information. In transformer, for example, if you have a picture here, okay, you have some pixels, and you want to know the attention. If this pixel is attending this pixel and this pixel, for example, maybe they are part of one object, or they are somehow they have the high mutual information within them. And so if you combine it with the idea of transformer, you can get very rich algorithm, because convolutional neural networks they care about local information. On the other hand, transformers I don't say global, but I say semi-local. But the future versions of transformers will care about global versions because we need text generation. We want to, when I say a word, we want the computer to generate a book for me. Each time I say that word, I want to generate a new book. So when I say, for example, philosophy, I want the bot to create different books about that. And that's why we need something more global. I mean, long-range dependencies between the words, because, as I said, your sentence could be huge. And so this is the future of transformers. And so you see that a kind of transformer is called BERT, or some other versions of transformers. Some people use it for GPT-2, now GPT-3 and 4 and N. And so new companies are using transformers for their own models. So there are lots of different ways to leverage transformers for future applications. And you can also use it for speech recognition. You can use it for text summarization. For example, today I talked about translation from German to English. You can translate it from any language to any other language. You can do, what else? You can do text summarization, speech recognition, translation, text generation, which is my favorite, text generation. You can do all sorts of things with transformers. And so in my next lecture, which is next weekend, I want to create a new playlist. I want to talk about information theory. Information theory. This is the title of my next playlist. Information theory of deep learning. You know, if you can also combine the concept of mutual informations, error correcting codes for transformers as well. So there are lots of ideas that you can use for transformers. And after I finished this playlist, which is about maybe 10 or 12 lectures, you will notice that you can use mutual information for transformers as well. Mutual information and more generally conditional mutual information. Because if you don't understand the information theory of your deep learning, and so these layers, each one, they pass information to the next layer, and we need to change this a little bit. Otherwise, we cannot improve transfer learning and meta learning and many new ideas in order to make deep learning more scalable. For example, I told you about knowledge distillation, that if you have a very complex deep neural net, then you can use knowledge distillation to have, for example, if it is a teacher model and this is a student model, you can use this to find a more simplified version of that complex model. Because you can put this on your iPhone, and your iPhone can can do very complicated computer vision task or NLP task or speech recognition task without connecting to any other things. Even you don't need cloud, because you do it on your simple computer or very simple laptop or iPhone. So that's why knowledge distillation is important. The other important technology, so in general, transfer learning can be used for NLP a lot, as I told you. And so the ideas of domain adaptation, these are very important in future, because domain adaptation nowadays is not mature yet, but in future we have some clues that if we combine it with information theory, you can get even much more interesting results than ideas of meta learning. And finally, I want to introduce you three of my favorite amazing scholars. One of them is Joshua Bengio. I think he works in Mila. The other one is Jeff Hinton. I think he works on Vector. Yes, Vector Institute. So Mila and Vector Institute are in Canada. And the third one I wanted to introduce you was the CTO of Facebook, Yann LeCun. We know him for convolutional neural networks. We know Jeff Hinton whenever we talk about restricted Boltzmann machine, also semantic hashing, also capsule neural networks. And when I think about Bengio, he wrote an article recently about graph transformers. And so these three guys are really there. For example, Yann LeCun, he has energy-based level. And what is energy-based level? Energy-based methods. You know that we have generative models. You have discriminative models. Generative models like variational autoencoder, generative adversarial neural networks, normalizing flow. Of course, this could be discriminative as well. So you can unify. So the goal of machine learning should be unification of all of these methods. What if you create a framework called energy that you can somehow unify all of these paradigms? Because if you unify paradigms, you get some pure ideas. And so generalization is not just making machine learning more beautiful, but because we want to understand what we haven't understood yet. So I think that's enough for today. All right, have a good night.